Oh, I lost my drift speed. VD, VD. If I divide both sides by the area, that cross-sectional area, I have current per unit area, as it comes through, is equal to Q in drift speed. And this is current density. And before I plunge further into this, let's take a look at units. Questions up to here? Now we generally think of, or I shouldn't say we, generally I think of current as this sort of monolith. Current density is constant and we have just charge flowing through it. But in reality, the closer the charge in the middle of the wire is going to be moving a little bit faster than the stuff at the edges, because I have an additional constraint at the edges where the electrons are not going to be leaping out like dolphins, porpoises, salmon. Name a fish that jumps out of water. In the ocean, what are the flying fish? What are the fishes that jump out of the water a lot? Flying fish? All right. It's not like they're flying fishes. The electron's not going to jump out and then come back in later on. Under normal situations. All right, units. Well, I have my equation over there for current, which is dq dt. What are the units of Q? And time? So units of current would be?
Coulombs per second.
So the unit of current is the unit of charge over the unit of time. So we have a coulomb per second. And this is too much for physicists to write, so they came up with the one-word thing. Unit for current, the traditional one. Amp, or amperes, capital A. Named after ampere, something like that. Now, might have been with the other class, I apologies if I've already said this bit. Now, in terms of base units, typically you deal in the presentation of it, you deal with coulombs first, and well, seconds first, then you deal with coulombs. So amperes seems like it's a derived unit. The way that the powers that be set it up is that coulomb actually is the derived unit, and that the coulomb is defined as an ampere second. Now, current density. What are the units of current density? The SI unit. It's not a one-word thing.
Amps per meter squared.
Yep. It is current, ampere per meter squared. This capital A and that capital A do not mean the same thing. This A here in the unit is amperes, this A in the formula is area. All right, I don't know what you're thinking. You're going, this is great, but where's the calculus? Well, here's some calculus. Suppose I have a wire with a current density of, because I already worked it out, 3 amperes per meter over R plus 1 meter, where the units of R is meter. And that would make meters on the bottom, so amperes per meter divided by meters, which is an ampere per meter squared. what I want to know is what is the current flowing through this wire. Now when R is, oh, I actually have to give a radius, I think. So this is a really thick wire, so this has an ultimate radius of 0.2 meters. R is defined as from my central axis here, so this is R. So when R is small, I have my maximum current. As R gets bigger, the current slows down. So if I'm looking at a cross section right here, my current would, well, crudely look something like that, where I could lose current in the middle. So to find current, I know that that's the non-calculus version of it, but this is di dA, so therefore di is equal to JDA. And we can integrate. So I have my current is equal to the integral of 3 over R plus 1 dA. Obviously, I have two variables here. R is the distance I am from my center there, and A, which is a differential, so it's considered a variable. I need to relate the two. This is looking down the barrel. There's my center, and I'm some distance R away. We have symmetry, angular symmetry, the fact that my value, my current here and my current here would be the same, or current density there and there are the same. So if I imagine a circle that is a distance R away from the center, I can now get a relationship between R and dA. So I take this infinitely thin circle. What is the area of that circle?
R squared.
That would be the area of O. I'm talking about the area of that line, not of a circle itself.
1/2 pi r squared.
Yeah.
That'd be 2 pi R.
Okay, that's how long it is. So 2 pi r. That's still one dimension. I need something else.
dr.
dr. If you think about this as just a ring, if I pull that ring out and I cut it, basically it's just a long piece of line here. The length here is 2 pi r. The thickness, well, that's a change in r there, so my thickness is dr. So it's like I have a rectangle with a length of 2 pi r and an infinitesimally thin width of dr. So this now becomes the integral 3 over r plus 1 times 2 pi r dr, which is 6 pi integral r over r plus 1 dr. And now we need limits of integration.
So dr is referred to that like tiny little section in the line.
Say it again.
Dr would be referred to that like tiny little section in the line.
Yeah, it's the dr is the thickness of that line.
Okay. Wait, thickness like this?
Yeah.
Okay.
So it's, even though this line, the circle here is infinitesimally thin, it's not zero. There is a thickness to it of, so well, since that's in the radial direction, the thickness there is dr. And I also, I guess we could have gone the way that Benjamin was leading us. If A is pi r squared, then dA would be 2 pi r dr. All right, so what are my limits of integration? All right, 0 to, I'm gonna put down big R for right now, and then we'll put in the 0.2 at the end. Right, so how do I integrate R over R plus 1?
U,
Count 2 problem here, pardon?
U substitution.
What would you set U equal to?
R.
If you set U equal to R, then I think you just basically end up with something that looks exactly like that, except it's a U instead of an R.
R plus 1.
I think that is a path to take. So if we let U equal R plus 1, then du equals dr. And so my integral of R over R plus 1 dr equals U minus 1 over U du. Now what? V substitution, probably not a good idea. I'm setting V equal to U minus 1.
We can separate it into two, correct?
Okay.
So it'd be 1 minus 1, or integral 1 minus the integral.
Let me actually split it apart more than that. So 1 du minus the integral of 1 over U du. All right. And so R goes from 0 to big R, so U is going to go from 1 to R plus 1. I'm sorry, 1 through R plus 1. Okay. Integral of du.
U.
So that's U from 1 to R plus 1. Minus integral of 1 over U.
ln U.
Natural log of U from 1 to R plus 1. And I still have that 6 pi over there, which I stopped writing. So that's going to be R plus 1 minus 1 minus the natural log of R plus 1 minus the natural log of 1. So that's just R right there. So we treat this a couple different ways, but what's the natural log of 1?
0.
So we're just with R minus the natural log of R plus 1. So my current, therefore, is 6 pi times 0.2 minus the natural log of 1.2. Which is something absolutely exciting.
Three, 2.
And speaking of which, and amps is fine, amperes is more formal, but I do want to state that I do not accept amperage as a real word. So, I know some people use it a lot, please don't. Current is easier to say, fewer letters, fewer syllables, the word is current. Another word that I really despise, utilize. I've yet to see a situation in which the word use does not serve the same purpose. All right, questions to hear? All right. Do recognize, again, we've had only one physics equation. All the rest is just math and definitions. Coulomb's law, the very first equation we started with. So again, we got this wire here. And what I want to look at is the current that's flowing through it. And we got as far as Q in what's the last one? Q in
VD.
thank you. Little serif right there. All right, so let's explore this just a little bit more. First off, if we're dealing with just normal current flow here, we're dealing with electron flow, so I know what the charge is, and I'm ignoring the sign. So E in a VD. Now let's try to figure out what exactly is the drift speed. If I have a particle that's coming in and it hits something and bounces, then hits and bounces, and it's bouncing everywhere, just slowly moving to the right. If I wanted to find, I know that my drift velocity is equal to my initial velocity plus AT, if my acceleration is constant. So I'm sort of concerned with, I think it's bad wording just then. The issue that we need to look at is between the bounces, because as soon as it hits something, the acceleration is going to change. So we're just looking at between the bounces. And I want to look at the average value. Well, the average time it takes between bounces is what is generally called the mean free time. Mean as an average, free as in it's not obstructed by anything, mean free time. And this is the average time it is between hitting other particles. Acceleration, I know, is force divided by mass. Well, we're dealing with an electron being moved by something. It's got to be moved by, well, there has to be an electric field present, otherwise it would not move. So this is going to be the charge times the electric field over mass. Or specifically for this problem, it's an electron moving. And I dropped the directional aspect of it just because, you know, just assume the wire's traveling straight, or the wire's straight. And my average initial velocity is 0. Because it's just as likely to hit something going this way and then bounce back as it is to be going this way and hit something and bounce forward. There's a randomness to it, so that in general, the average value of this is 0. So I can come up with my drift speed. My average drift speed is my acceleration times the amount of time it takes between. So this is E little n A times E electric field tau over m. So E squared n m tau times A E. And that A is the cross-sectional area, that E is the electric field strength. Now the thing I've got in parentheses there. That mass is the mass of the electron. That E is the charge of an electron. N is the charge, total charge carrier density. Tau is the mean free time. Two of them are relatively, well, in classical physics are constants. That's the mass of the electron. These two have set values. Unless, of course, you're in high energy physics, but we're not there. N and tau are dependent upon the material. So if I know a specific material I'm working with here, that whole thing in front is just a constant that is material specific. So this is a material specific constant, this whole thing. And it is represented by a lowercase sigma. This is conductivity. So I've now broken that down into my current flowing through it is equal to the conductivity times the cross-section